In this video, we're going to continue our discussion of the well-architected framework, and the next pillar is reliability. The reliability pillar includes the ability of a system to recover from infrastructure or service disruptions, dynamically acquire computing resources to meet demand, and mitigate disruptions such as misconfigurations or transient network issues. The reliability pillar provides an overview of design principles, best practices, and questions. The first design principle of the reliability pillar is test recovery procedures. In an on-premises environment, testing is often conducted to prove the system works in a particular scenario. Testing is not typically used to validate recovery strategies. In the cloud, you can test how your system fails, and you can validate your recovery procedures. You can use automation to simulate different failures or to recreate scenarios that led to failures before. This exposes failure pathways that you can test and rectify before a real failure scenario, reducing the risk of components failing that have not been tested before. You should also automatically recover from failure. By monitoring a system for key performance indicators, you can trigger automation when a threshold is breached. This allows for automatic notification and tracking of failures, and for automated recovery processes that work around or repair the failure. With more sophisticated automation, it's possible to anticipate and remediate failures before they occur. You should also scale horizontally to increase aggregate system availability, and replace one large resource with multiple small resources to reduce the impact of a single failure on the overall system. You should distribute requests across multiple, smaller resources to ensure that they don't share a common point of failure. Next, you should stop your guessing capacity. A common cause of failure in on-premises systems is resource saturation, when the demands placed on a system exceed the capacity of that system. In the cloud, you can monitor demand and system utilization and automate the addition or removal of resources to maintain the optimal level to satisfy demand without over or under provisioning. And finally, you should manage change in automation. Changes to your infrastructure should be done using automation. The changes that need to be managed are changes to the automation. To achieve reliability, a system must have a well-planned foundation and monitoring in place, with mechanisms for handling changes in demand or requirements. The system should be designed to detect failure and automatically heal itself. There are several best practices associated with reliability, and the first is foundations. Before architecting any system, foundational requirements that influence reliability should be in place. For example, you should have sufficient network bandwidth to your data center. These requirements are sometimes neglected because they are beyond a single project scope. This neglect can have a significant impact on the ability to deliver a reliable system. In an on-premises environment, these requirements can cause long lead times due to dependencies and therefore must be incorporated during initial planning. With AWS, most of these foundational requirements are already incorporated or may be addressed as needed. The cloud is designed to be essentially limitless, so it is the responsibility of AWS to satisfy the requirement for sufficient networking and compute capacity, while you are free to change resource size and allocation, such as the size of storage devices on demand. AWS sets service limits, which are an upper limit on the number of each resources your team can request to protect you from accidentally over-provisioning resources. You'll need to have governance and processes in place to monitor and change these limits to meet your business needs. As you adopt the cloud, you may need to plan integration with existing on-premises resources. A hybrid model enables the gradual transition to an all-in cloud approach over time. Therefore, it's important to have a design for how your AWS and on-demand resources will interact as a network topology. The next best practice is change management. Being aware of how change affects a system allows you to plan proactively, and monitoring allows you to quickly identify trends that could lead to capacity issues or SLA breaches. In traditional environments, change control processes are often manual and must be carefully coordinated with auditing to effectively control who makes changes and when they are made. Using AWS, you can monitor the behavior of a system and automate the response to KPIs, for example, by adding additional servers as a system gains more users. You can control who has permission to make system changes and audit the history of these changes. When you architect a system to automatically add and remove resources in response to changes in demand, this not only increases reliability, but also ensures that business success doesn't become a burden. With monitoring in place, your team will be automatically alerted when KPIs deviate from expected norms. Automatic logging of changes to your environment allows you to audit and quickly identify actions that might have impacted reliability. Controls on change management ensure that you can enforce the rules that deliver the reliability you need. The next reliability best practice is failure management. In any system of reasonable complexity, it's expected that failures will occur. It's generally of interest to know how to become aware of these failures, respond to them, and prevent them from happening again. With AWS, you can take advantage of automation to react to monitoring data. For example, when a particular metric crosses a threshold, you can trigger an automated action to remedy the problem. Also, rather than trying to diagnose and fix a failed resource that is part of your production environment, you can replace it with a new one and carry out the analysis on the failed resource out of band. Since the cloud enables you to stand up temporary versions of a whole system at low cost, you can use automated testing to verify full recovery processes. You should regularly back up your data and test your backup files to ensure you can recover from both logical and physical errors. A key to managing failure is the frequent and automated testing of systems to cause failure, and then observe how they recover. Do this on a regular schedule and ensure that such testing is also triggered after significant system changes actively track KPIs, such as the recovery time objective and recovery point objective, to assess a system's resiliency. Tracking KPIs will help you identify and mitigate single points of failure. The objective is to thoroughly test your system recovery processes so that you are confident that you can recover all your data and continue to serve your customers, even in the face of sustained problems. Your recovery processes should be as well exercised as your normal production processes. Finally, there are a few key services that are going to help you most when applying the reliability factor to your well-architected framework. For your foundations best practice, IAM and Amazon VPC are going to help you maintain your solid foundation. AWS CloudTrail, Config, and CloudWatch will help you keep an eye out on your change management. And then CloudFormation and S3 will help you both record and impact your failure management. The next pillar of the well-architected framework is performance efficiency. The performance efficiency pillar includes the ability to use computing resources efficiently to meet system requirements and to maintain that efficiency as demand changes and technologies evolve. There are a few design principles for the performance efficiency pillar, and the first is to democratize advanced technologies. Technologies that are difficult to implement can become easier to consume by pushing that knowledge and complexity into your cloud vendor's domain. Rather than having your IT team learn how to host and run a new technology, they can simply consume it as a service. For example, NoSQL databases, media transcoding, and machine learning are all technologies that require expertise that is not evenly dispersed across the technical community. In the cloud, these technologies become services that your team can consume while focusing on product development rather than resource provisioning and management. Another design principle is being able to go global in minutes. You should easily deploy your system in multiple regions around the world with just a few clicks. This allows you to provide lower latency and a better experience for your customers at minimal cost. Next are serverless architectures. In the cloud, serverless architectures remove the need for you to run and maintain servers to carry out traditional compute activities. For example, storage services can act as static websites, removing the need for web servers, and event services can host your code for you. This not only removes the operational burden of managing these servers, but can also lower transactional costs because these managed services operate at cloud scale. Next, you should experiment more often. With virtual and automatable resources, you can quickly carry out comparative testing using different types of instances, storage, or configurations. And finally, Your last design principle for performance efficiency is mechanical sympathy. You should use the technology approach that aligns best to what you are trying to achieve. For example, consider data access patterns when selecting database or storage approaches. You should take a data-driven approach to selecting a high-performance architecture. You should also gather data on all aspects of the architecture, from the high-level design to the selection and configuration of resource types. By reviewing your choices on a cyclical basis, you'll ensure that you are taking advantage of the continually evolving AWS cloud. Monitoring will ensure that you are aware of any deviance from expected performance and can take action on it. Finally, your architecture can make trade-offs to improve performance, such as using compression or caching, or relaxing consistency requirements. Your first best practice for performance efficiency is selection. The optimal solution for a particular system will vary based on the kind of workload you have, often with multiple approaches combined. Well-architected systems use multiple solutions and enable different features to improve performance. In AWS, resources are virtualized and are available in a number of different types and configurations. This makes it easier to find an approach that closely matches your needs, and you can also find options that are not easily achievable with on-premises infrastructure. For example, a managed service such as Amazon DynamoDB provides a fully managed NoSQL database with single-digit millisecond latency at any scale. When you select the patterns and implementation for your architecture, use a data-driven approach for the most optimal solution. Your architecture will likely combine a number of different architectural approaches. The implementation of your architecture will use the AWS service that are specific to the optimization of your architecture's performance. The next best practice is compute. The optimal compute solution for a particular system may vary based on application design, usage patterns, and configuration settings. Architectures may use different compute solutions for various components and enable different features to improve performance. Selecting the wrong compute solution for an architecture can lead to lower performance efficiency. In AWS, compute is available in three forms: instances, containers, and functions. And of course, we've covered all of those in previous videos in this course. But just as a quick extra overview, instances are virtualized servers, and therefore you can change their capabilities with a click of a button or API call. Because in the cloud resource decisions are no longer fixed, you can experiment with different server types. At AWS, these virtual server instances come in different families and sizes that we've covered. Containers are a method of operating system virtualization that allow you to run an application and its dependencies in resource-isolated processes. Functions abstract the execution environment from the code you want to execute. For example, like we've covered in this course, AWS Lambda allows you to execute code without running an instance. The next best practice pertains to storage. The optimal storage solution for a particular system will vary based on the kind of access method. Well-architected systems use multiple storage solutions and enable different features to improve performance. In AWS, storage is virtualized and is available in a number of different types. This makes it easier to match your storage methods more closely with your needs, and also offers storage options that are not easily achievable with on-premises infrastructure. For example, Amazon S3 is designed for 11 nines of durability. You can also change from using magnetic hard disk drives to solid-state drives, and easily move virtual drives from one instance to another in seconds. And our next best practice pertains to databases. The optimal database solution for a particular system can vary based on requirements for availability, consistency, partition tolerance, latency, durability, scalability, and query capability. Many systems use different database solutions for various subsystems and enable different features to improve performance. Selecting the wrong database solution and features for a system can lead to lower performance efficiency. Amazon RDS provides a fully managed relational database. With RDS, you can scale your database's compute and storage resources, often with no downtime. Amazon DynamoDB, as we've covered, is a fully managed NoSQL database that provides single-digit millisecond latency at any scale. Redshift is a managed petabyte scale data warehouse that allows you to change the number or type of nodes as your performance or capacity needs change. Although a workloads database approach has significant impact on performance efficiency, it's often an area that is chosen according to an organizational default rather than through a data-driven approach. As with storage, it's critical to consider the access patterns of your workload and also to consider if other non-database solutions could solve the problem more efficiently. And our final best practice for performance efficiency pertains to networks. The optimal network solution for a particular system will vary based on latency, throughput requirements, and so on. Physical constraints, such as user or on-premises resources, will drive location options, which can be offset using edge techniques or resource placement. In AWS, networking is virtualized and is available in a number of different types and configurations. This makes it easier to match your networking methods more closely with your needs. AWS offers networking features through a number of services like Amazon Route 53 and Amazon VPC. As a quick review, when architecting solutions, there is a finite set of options that you can choose from. However, over time, new technologies and approaches become available that could improve the performance of your architecture. Using AWS, you can take advantage of continual innovation which is driven by customer need. When you architect solutions, you should think about trade-offs so you can select an optimal approach. Depending on your situation, you could trade consistency, durability, and space versus time or latency to deliver higher performance. Using AWS, you can go global in minutes and deploy resources in multiple regions across the globe to be closer to your end users. You can also dynamically add read-only replicas to information stores such as database systems to reduce the load on the primary database. And as we've covered, AWS also offers caching solutions such as Amazon ElastiCache, which provides an in-memory data store or cache, and CloudFront, which caches copies of your static content closer to end users. And the final pillar of the well-architected framework is cost optimization. The cost optimization pillar includes the ability to run systems to deliver business value at the lowest price point. There are a few design principles under the cost optimization pillar, and the first is that you should adopt a consumption model and pay only for the computing resources that you require and increase or decrease usage depending on business requirements, not by using elaborate forecasting. For example, development and test environments are typically only used for 8 hours a day during the work week. You can stop these resources when they're not in use for a potential cost savings of 75%. The next design principle is to measure overall efficiency. You should measure the business output of your system and the costs associated with delivering it. Using this measure will help you understand the gains you make from increasing output and reducing costs. You should also stop spending money on data center operations because AWS does the heavy lifting of racking and powering service for you so that you can focus on your customers and business projects rather than on infrastructure. Next, you should analyze and attribute expenditure. The cloud makes it easy to accurately identify the usage and cost of systems, which then allows transparent attribution of IT costs to individual business owners. This helps measure return on investment and gives system owners an opportunity to optimize their resources and reduce costs. And finally, you should use managed and application level services to reduce your cost of ownership. In the cloud, managed and application level services remove the operational burden of maintaining servers for tasks such as sending email or managing databases. As managed services operate at cloud scale, they can offer a lower cost per transaction or service. As with other pillars, there are trade-offs to consider. For example, do you want to optimize for speed to market or for cost? In some cases, it's best to optimize for speed, going to market quickly, shipping new features, or simply meeting a deadline rather than investing in upfront cost optimization. Design decisions are sometimes guided by haste as opposed to empirical data. as the temptation always exists to overcompensate just in case rather than spend time benchmarking for the most cost-optimal system over time. This often leads to drastically over-provisioned and under-optimized deployments, which remain static throughout their lifecycle. The following sections that I'll talk about provide techniques and strategic guidance for the initial and ongoing cost optimization of your deployment. The first best practice for cost optimization is using cost-effective resources. Using the appropriate instances and resources for your system is key to cost savings. For example, our reporting process might take 5 hours to run on a smaller server, but 1 hour to run on a larger server that is twice as expensive. Both servers give you the same outcome, but the smaller server incurs more cost over time. A well-architected system uses the most cost-effective resource, which can have a significant and positive economic impact. You also have the opportunity to use managed services to reduce costs. For example, rather than maintaining servers to deliver email, you can use a service that charges on a per-message basis. AWS offers a variety of flexible and cost-effective pricing options to acquire instances from EC2 and other services in a way that best fits your needs. We've talked about these before, but just as a quick extra review, on-demand instances allow you to pay for compute capacity by the hour with no minimum commitments required. Reserved instances allow you to reserve capacity and offer savings of up to 75% of on-demand pricing. With spot instances, you can leverage unused EC2 capacity and get savings of up to 90% off. Spot instances are appropriate where the system can tolerate using a fleet of servers where individual servers can come and go dynamically, such as stateless web servers, batch processing, or when using big data. Appropriate service selection can reduce usage and costs, such as CloudFront to minimize data transfer or completely eliminate costs, such as using Amazon Aurora on RDS to remove expensive database licensing costs. Your next best practice for cost optimization is matching supply and demand. Optimally matching supply to demand delivers the lowest cost for a system, but there also needs to be sufficient extra supply to allow for provisioning time and individual resource failures. Demand can be fixed or variable, requiring metrics and automation to ensure that management does not become a significant cost. In AWS, you can automatically provision resources to match demand. Autoscaling and demand, buffer, and time-based approaches allow you to add and remove resources as needed. If you can anticipate changes in demand, you can save more money and ensure your resources match your system needs. You should also consider expenditure awareness. The increased flexibility and agility that the cloud enables encourages innovation and fast-paced development and deployment. It eliminates the manual process and time associated with provisioning on-premises infrastructure, including identifying hardware specifications, negotiating price quotations, managing purchase orders, scheduling shipments, and then deploying the resources. However, the ease of use and virtually unlimited on-demand capacity may require a new way of thinking about expenditures. Many businesses are composed of multiple systems run by various teams. The capability to attribute resource costs to the individual business or product owners drives efficient usage behavior and helps reduce waste. Accurate cost attribution also allows you to understand which products are truly profitable and allows you to make more informed decisions about where to allocate budget. In AWS, you can leverage Cost Explorer to track your spend and gain insights into exactly where you spend. Using AWS budgets, you can send notifications if your usage or costs are not in line with your forecasts. You can also use tagging on resources to apply business and organization information to your usage and cost, which provides additional insights to optimization from an organization perspective. You can use cost allocation tags to categorize and track your AWS usage. When you apply tags to your resources such as EC2 instances and S3 buckets, AWS generates a cost and usage report with your usage and your tags. You can apply tags that represent business categories to organize your costs across multiple services. Combining tagged resources with entity lifecycle tracking makes it possible to identify orphaned resources or projects that are no longer generating value to the business and that should be decommissioned. You can also set up billing alerts to notify you of predicted overspending, and the AWS Simple Monthly Calculator allows you to calculate your data transfer costs. Another pillar is optimizing over time. As AWS releases new services and features, it's a best practice to review your existing architectural decisions to ensure they continue to be the most cost-effective. As your requirements change, be aggressive in decommissioning resources, entire services, and systems that you no longer require. Managed services from AWS can often significantly optimize a solution, so it's essential to be aware of new managed services and features as they become available. For example, running an Amazon RDS database can be cheaper than running your own database on EC2. And finally, for the key resources that you'll use for cost optimization, the absolute most essential is Cost Explorer through your billing dashboard, which will help you gain visibility and insights into your usage across your systems and throughout your business. And that'll about wrap it up for our summary of the well-architected framework. So if all of that makes sense, then feel free to move on.